Welcome back, everybody. In this video, what I want to do is talk about decision trees again. And we've done this previously. We talked about decision trees, and I want to do a very quick review of a decision tree. And in this video, I just want to take a deeper dive into a couple aspects of decision trees. And, we have talked about the different algorithms in machine learning and how they're broken up into three groups, right? We've got linear models. We've talked about, we've started down a path of neural networks that we're going to come back to, but then we've got this tree-based model. Okay. And with the tree-based models, we really get into this decision tree and a random forest, but there's also this gradient boost idea, but I'm not going to really worry about that right now. I just want to focus on decision tree and random forest. Okay. And so, a decision tree can produce some sort of a diagram of a course of action, okay, or a decision that can be made. And, we use these decision trees because we want to make predictions, but what predictions can we make with this decision tree? And we've got two sort of scenarios. We can do regression, and that gives us a value of an output. And so it's used when the dependent target variable is numerical or continuous, like housing prices. Okay. And the other one is classification. So true, false, yes or no. And we determine a set of if-then conditions which help us classify something like the iris database. So really quickly, let's look at some advantages of the decision tree. And the first one is data preparation is really easy. Okay, that's kind of self-explanatory, really. We can process both numerical and categorical data. And we'll see this as, some examples. It's simple to visualize. And it's even more simple to interpret what's going on. And, lastly, performance is not affected by non-linear parameters. Okay, so these are some of the advantages of a decision tree. And of course, we've got to talk about a disadvantage of a decision tree. Your algorithm can capture noise and cause overfitting. Okay, so you got to be careful for that. You got to be aware that it can happen. Highly complex decision trees can result in a low bias tree, causing modeling challenges with the new data. Okay, so that's a big disadvantage. And then finally, the model can become unstable due to high variance in the data. Okay, so we'll look at this in some different examples. Okay, and I want to talk about this idea, this entropy. Okay, and entropy is a measure of unpredictability or randomness in the data. So let's look at an example here. So we have 4 different types of buildings. We have a high-rise condo. We've got a small, old apartment building, relatively modern house, and, big skyscrapers from the 30s. To me, that I think is the Empire State Building. And, when we talk about a measure of unpredictability or randomness in the data, we're still sort of in a classification, right? This is all architecture, or these are all buildings. But if we look at the first thing here, is the style modern? Okay, we look at this and we say, oh, I'm not so sure. You could say that these two here, their style is modern. So they go into the true side. The other two, is their style modern? And the answer would be no. I think the Empire State Building was probably built in the 20s. I'm pretty sure it was built in the 20s. I could be wrong. But is it modern? No. Now, what about the height? Is the height greater than 450 meters? And so for the high-rise condo, yes, but for the house, no. Okay, if we look at this, are these buildings greater than 450 meters? The Empire State Building is, and this other building is not. Okay, so what does this say? This says that the top level here is something referred to as high entropy. Okay, so the first sort of layer there is high entropy. And then as we split it or we subdivide it, we start to lower our entropy until we get to a point where we can no longer split the data anymore. And so when we've split the data to the lowest level, we say it has no entropy, right? So there's no randomness in the data. So it's important that you kind of understand this concept of entropy when we're doing decision trees. And so there's this other term that we need to understand. It's something called information gain. And it is a measure of decrease in entropy after a split. So in other words, after you've split this, how do we measure the decrease in the entropy? And we've got this first level, and we're going to say this is entropy 1. And then we split it and we go down to the next level, and that is something we refer to as entropy 1. And then, when we split that, we have to measure our information gain. And the way we do that is that entropy 1 is subtracted from entropy 2. And that's going to define our gain. Okay. So if we look at this example, we see more of this, but there's a few more definitions I want to get to first. And the bottom one that we have here is our leaf node. This is the lowest level decision or classification that we can get from this. This becomes our leaf node, the lowest layer. Okay, and of course the uppermost layer is our root node. So we've got a root node at the top and basically a leaf node at the very bottom. And it's no wonder that we call these trees, right? And so how does this really work? So we want to make a prediction. And so we classify different types of buildings based on their features. And we use a decision tree to do this. So right off the top, we know that this first layer, this root node, is high entropy. It has high entropy. But if we put this into a table and we break it down into different components, we can start to figure out how we're going to arrive at a prediction. Okay, so you see that the style of the building is, let's say, classic, postmodern, modern, and classic again in their height features. We've got 450, 7, 450 again in 15. So we can break out those things. And then we have finally this label, okay, which is our office, apartment, a house, an office, an apartment again. So we're creating this table based on the high entropy that we have for the given data set. And, our task really is to frame the conditions that split the data into, to get the highest information gain. So that's really our goal, is to get the highest information gain. So we've got this awesome calculation formula for entropy. And it looks pretty horrific to me, I'll be honest with you. But, let's look at this data for a minute. And suppose we have a number of samples. So you can see here, I've got 3 high-rise condos. I've got 2 old-fashioned apartment buildings. I've got 1 modern-looking house. And I've got 2 old skyscrapers, right? And when you add up the number of samples that you have, you actually come to, in this case, 8 samples. Okay, and so when we look at our entropy, how do we translate this really scary looking formula into a calculation for entropy? Well, we basically do this. The key number that we really need here is that value for number 8. We really need that, because when we plug that into this formula, we get this, and, we just continue to take that formula and, plug in our sample from each over the actual total number of the sample size. And we're doing this log calculation. And it's as simple as that, really. Okay, the beauty is with programming is we actually have functions that will take care of that. Okay, we're not going to hard code this stuff. So you can see here this long-winded formula. this is really what's under the engine here, or under the hood, to see what it is. And this comes out with a calculation of 0.571. That's the entropy for that particular example right there. So if our task is to frame the conditions that split the data to the highest information gain, then we want to split the data using each condition and then check that gain. And so the condition that gives us the highest gain will be used to make the first split. And so what does that really mean ultimately? So if I look at my data set again, right, there's high entropy here. And I put that into that chart that I showed previously. When I start to look at this and really kind of pick through that data a little bit, I can break down all these different conditions. So I've got my style is modern. My height is greater than or equal to 450 meters. Is my style postmodern? Is my style classic? What if my height is less than 450 meters? Right. And so when I look at this first one here, I can really tell that the condition that gives me my maximum gain is my style. I'm choosing my style, but this is something that I want to come back to that I mentioned in the beginning, which was some of the disadvantages. Okay, and here's one of the disadvantages of doing this right now. It's highly complex decision trees can result in a low bias tree, causing modeling challenges with the new data. But, this isn't overly complex in this particular case. But what I want to do is look at this and say, well, why is it that I'm choosing style equals modern? Okay, because style equals modern only shows up once on my little chart there under modern. Okay, and this is where you've got to really look at the data and figure out what you think makes the most sense, what's going to give you your maximum gain. Okay, and so in this particular case, I'm looking at this, and to me, it does seem a little obvious that style equals modern will give me that first gain that I want. But to you, you may look at it and say, well, style equals classic. Okay, so there could be a difference in the interpretation of this. So when we look at this complexity of the decision tree, that's one of the issues. Now, in my case, I've chosen style equals modern. Okay, but what you can see here is that my entropy is decreasing, but we still need to split at both branches to get entropy to 0. So I've got to still split this again with another condition. And in this case, my condition is based on the height. Okay, so my least value. So each branch has a single label. Okay, and so therefore entropy is going to be at its least value. And this is where I can make my 100% prediction. Okay, so now once I get it to this actual state, now I can be ready for prediction. Okay, so that's really what that's all about. So in this example, we're going to try to make a prediction. Will the customers repay the loan they took from the bank? And we're going to use a decision tree to do this. So what I'm going to do is I've opened up my Anaconda, and I'm going to change the title right away. So I'm going to say bank loan decision tree. Okay, so that's what we're going to call this one. Okay, and as always, I need to do my normal import. So I'm going to import NumPy. Now from here, what I need to import is a couple of really good tools from our sklearn. Okay, so the next 4 that come out of here are going to come from sklearn. And this is really good. Like, this is the kind of stuff that we really like about Python, because all of these classes have been written for us to do all this heavy lifting. So we don't have to actually go and do it hydraulically. Okay, so what I'm going to do is I'll just type in all of them that we need to have in here. Now, keep in mind, I think the very first video I ever did with this was a decision tree. Okay, and so some of this is going to be familiar to us, which is great. So let's get into that. But now that we've done more of a theoretical overview of it, that's why I wanted to come back and revisit this and see what's really going on again. Okay, so I'm going to just type in all the sklearn classes that we need to bring in. And you can see this model selection. I hit the tab and I'm going to go with model selection. And again, I can't stress enough to always use your tab, or it's in other IDEs, it's referred to as IntelliSense. Go and get it. Use it, because if it doesn't show up, it might tell you you've got some sort of an issue. But if it does show up by using tab, that's a good sign that you're on the right track. So what I did is I typed in train and then tab, and then test split came in. That's an import. So that told me that, hey, I'm on the right track here. So from, so this one will be a dot tree tab, and it's there. Okay. So decision tree classifier. Okay, I've got two options when I hit tab. I want decision tree classifier. Okay. And this one is metrics. Okay, I want the metrics here. And import accuracy score. Okay, and it showed up with my tab, which is great. And my last one here is import a tree. Just this, just a tree. Okay. All right, now we're going to get into loading the data. Okay, so load. And I already have a file in here. And it's just called bank. Okay, and then we're going to look at what's inside the bank. You know, what are the items that we have inside there? So again, start on the right side if you can, and then assign it to something. So pd.read underscore CSV. And then in here, you want double quotes, bank. Now you're going to, if you're following along, you're going to have to come up with your own CSV file. Okay. I'll post this in Blackboard as well, but if not, come up with your own CSV for this, and we'll look at the headings that you might want to have. Okay. Here we're going to do our sep. Okay. So separate equals single brackets and comma. Okay, separated by that, do another comma and say header equals 0. Okay, so that's all that is to that line. So now we're going and we're saying, go and get that. Now I want you to assign it to something. And I'm just going to call it, bank data. And I'll put a underscore there. Okay, so bank data is now representing all of that. So let's go and see what this looks like. Print, and inside my print statement, data set length. And colon, just to give me a little bit of space there. And of course this, bank data. Put that in there, just like that. I'm good. Now I'm going to print the next line, and in my next line, I'm going to do data shape. Okay. Okay, I put a colon in there and a little bit of a space, and I think a comma there, and then we'll just go with bank data dot shape. Okay, so we've done this many times already. So let's just really quickly run this and see what we've got. Okay, so this particular data set has a length of 11,162 and a shape of 6. Okay, so I'm just going to really quickly show what it is in each of the columns here. Okay, and bank data dot head, and it really just looks like this. So I'll run that, and I run this, and you can see what's happening here. That I've actually got a lot of stuff going on in here, and I'm going to clean this up a little bit. I'm actually going to take this out of here. I'm going to put it onto the next line, and I'll use it as a function there. And let's see if we rerun this and clean it up a little bit. Okay, so I'm only going to look at the first 6 rows here. Actually, 5. I'm not really sure it's going to make too big of a difference, but what I want to point out is, loan, age, balance in their current bank account. Do they own a house or rent right now? Are they educated? Are they married? Okay, so this is pretty random stuff here, right? And again, this is when we're talking about the entropy, like how are we making selections on entropy? So it gets a little bit convoluted, right? And so for now, what I want to do is let's go put in a comment here. So I'm going to separate our sample size with our targeted variable. And, the way we've done this typically in the past is we've said X, capital X, is bank. Let's see what it gives us. So bank data dot values. Okay, and here we're going to do the square brackets, but we're going to put in our colon, not the semicolon, the colon, and then a comma. So what we're saying is go grab all of the samples, the entire sample size. And then from here, what I want to do is say, grab me columns 1 to whatever I want to choose. So I don't need the first one here. I don't need this 1, 0, 1, 2, 3, 4. So I want all of these ones here, and it looks like there's 6. So let's see if I can get away with doing 6. So I want from 1 to 6. Okay. And then from there, what I'm going to say is lowercase y is going to be my the values that I want next. And I only want one sort of output to that. Okay. And in this, I'm going to say bank data dot values. And in these brackets, I'm just going to go again, just like this, sorry, colon, comma, and here I'm going to put in a 0. Okay. Let me put in a note here. Y is bank loan data. So I'm just kind of making a little bit of notes, but code that can be kind of tweaked as well. It's just a different way of doing it. So I'm going to say bank tab. Doesn't let me do it this way because of the, I think the number sign. So bank data. And in here, I can say, I can put in a label really is loan. Okay. Now let's go here and split the data set into test and train. Okay. So this is a long line of code right now, but let's just go with it. Okay, and so this one is very familiar to us from what we've seen in the past. So X train, and of course there's no, I can't use the tab on this because it's on the left side right now, and I haven't declared it. I'm doing that now. So X train, comma, capital X underscore test, comma, and this will be lowercase y underscore train, comma, and lowercase y underscore test. Okay, and all of this is going to be equal to train test split. So if I say train tab, it gives me my test split, which is always encouraging, right? So now I'm going to say capital X, comma, lower y, And I want to divide it into a 70-30 split. Okay, so my test underscore, what does it give me? Will it give me anything? It doesn't look like it's given me anything with the tab. It's probably because it's inside the brackets, but I'm going to say my test size is going to be equal to 0.3. I'll just leave it at 0.3. And then a comma for my random state. Yeah, and it doesn't work because I'm inside the brackets. And that is going to equal 10. I'm actually going to change that to 100. And that's the random state. So it's just going to select random rows that it wants to do this with. So the next thing I want to do now is I need to address our entropy. Okay, and just remember, like, we spent a lot of time on the theory part of this talking about entropy. And I'm going to do the right side, then I'll come back and assign it to something on the left. So first thing I want is a decision, and it's decision tree classifier. Okay, and this is what pops up from hitting tab. And this is a function. And within that function, you know, there are different arguments that we can pass into this, and we're going to do that throughout this. Okay. So the first parameter in this is going to be something called a criterion or criteron, however you want to pronounce it. So let's see if it, yep, there it is. So I started CRI, I hit the tab, it actually selected it. So that's always a good thing. And in brackets, I'm going to say entropy. Okay. And the next thing I want to do is the random state again. And so after the comma, I'm going to say random state equals. We'll do that to 100. Okay. And let's put in a comma, and then we're going to say maximum depth. So, you know, how many times do we want to split this down? So I can say max depth right here. And you see the options that it's giving me. Max depth equals, max features equals, or max leaf nodes. Okay, so in this case, I'm going to pick max depth. Okay, so max depth, I'm just going to go with 3 for now. Okay, and then the final one is going to be my minimum sample leaf, or samples leaf. Okay, and this one here, I'm just going to say as my minimum samples leaf, I'm going to say 4. Okay, and so you can experiment with these things if you want, and try to get some more accuracy out of this. And so I told you that I'm doing the right side of the equation. Now I'm going to do the left side. So here we're going to see CLF, okay, underscore entropy. Okay, and you know, that's the one I'm going to do right now. And CLF is just really like class of entropy. So we'll do it again, CLF underscore entropy. And we're going to do dot fit. And in here in this argument list, because fit is a function, we'll say x underscore, what do we want? Train or test? We want train. And what's our output going to be is y underscore train. Okay, so we've got x train and y train. And so when I go ahead and I run that, and I'm going to run it from the top, and you got to get in the habit of running it from the top, because if not, you make changes in one of these cells, it doesn't actually remember that you compiled the stuff above it. So we'll just go down, and what you're seeing here is this output 18 is decision tree classifier. So it's telling you all of the stuff that's going on inside of here. So all it's really doing is printing out all of the different components of this decision tree classifier, right? And in this particular case, because we've only used so few of them, we've only used the 4. We're not getting any errors or anything like that. So the good news is that this is just kind of replicating what we're already saying anyway here. So let's continue on and do a function to actually finally make our prediction. Okay, and so the way we want to do that, and I'll just put a comment in there. The way we want to do that is we're going to say y underscore pred for predict entropy. Okay, and then this one is going to be CLF tab entropy dot predict. So I just typed in pred. I'll select the one that it gives me. And for my argument, I want to pass in my x test. Okay, so based on the test, make a prediction. So now I'm going to do print, and inside my print function, I'm going to just take this. Okay, copy, put that in there, and I'm going to print this out. And let's go ahead and run this. And what we're getting is really not much. We're not really seeing much of a prediction, are we? So, we know that what we're saying is that we're going to have at least 4 leaves, okay? And we're going to have a minimum depth. So basically, how many times are we going to split this entropy? Maximum time is going to be 3 times. Okay, so it's not surprising to me that we're not getting a great output here based on the fact that we have over 11,162 examples. So we've got a huge data set, but when we kind of look at this and we're only taking a very shallow depth to this, it's not surprising we're not getting a great output at this point. Okay, so just for fun, let's see what happens. Can I change this to 4? And does that make an impact in any way? Not really. What about this? Change this to 5. Will that make any impact? Okay, nothing really obvious right now. Okay. So, to consider something that if this was actually being used by the bank itself to make this prediction, this value right here, this X test, is what you would be hoping to predict right here. Like based on everything else that you've done, this is going to be the prediction coming out of your machine learning algorithm here. This is going to predict whether or not you should give a loan to this next person. So you're not seeing the actual full output of this. This is 0 and 1. If we go back and we looked and we say, okay, loan, no loan versus we're looking for 1 or a 0. So if it's a 1, we're saying yes, give them a loan. If it's a 0, we're saying no, we don't want them to have a 0. But in this particular case, because there's over 11,000 samples, and we're taking 30% of the 11,000, it's kind of truncated in this fashion here. But what I really want to do is not focus on the individual, like yes, no, yes, no. What I want to do is really just check the accuracy of my prediction, right? So I want to check my accuracy here. And the way I'm going to do that is I'm just simply going to call the accuracy score function from the sklearn library. Okay, so let's do this print, and inside here we're going to say, accuracy is, put a colon in there, a space, and I'm going to call the accuracy score. Okay, it's right there. It's in the tab, accuracy score, and I call that function, and I'm going to say my first argument is going to be y underscore test. Okay, my comma, y underscore tab, and I want to do predict entropy. And to make this a percentage, I just need to multiply it by 100. Okay, and that should be all I need to get the accuracy of my model. So let me go ahead and run that and see if we get a decent number. Okay, so based on the 11,162 samples, my accuracy for this is about almost 86%. Now, if I start messing around here, let's just say let's change this to 40. Let's make it a 60-40 split. See if that has an impact. Marginal impact, not too much. Do I wanna split this a little bit less? Let's see what happens here. Not a really big change there. I don't know if this makes sense. Now I'm just kind of playing around. I'm not doing anything overly complicated here, right? Let me see. Do I want to split this? Let's say 5 times. 7. I'm just guessing here. Did it change my accuracy? Not really. Not much of a change. Let's go from the top, run it all again from the top, and see if my accuracy changed. Not really a huge improvement there in terms of my accuracy, right? The one more thing I'll do, let me reduce this down. Let's just try this and see what happens. Okay, how many random samples are we going to take? That seemed to have a minor negligible impact as well. So anyway, this is a good example of a decision tree based on banking information. Okay, not overly complicated. You know, by all means, don't use this to take to your banking boss on Monday. Anyway, let's move on and start looking at random forest. So we're back in the slides and we're going to talk about random forest. And random forest involves a decision tree that can produce a diagram of a course of action, just like the previous one we did. Okay. And so when we look at this particular example, we're seeing a very high entropy example of our root node here. But when we split this data into 2, what you're seeing is a set. Okay, so there's just a different set of the data. And then we split it into the second set of the data. And this is kind of where you're getting the idea of random forest. Like, what does random forest really mean? It just literally means you're kind of poking through the forest looking for a way to split up your data. Okay, so that's kind of the easiest way to state that. So we know at the top, we've got high entropy. Okay, and then as we split, we get into lower entropy or low entropy. So we'll say the first is entropy 1, and these other 2 are entropy 2s. Okay, so they're both equal in terms of their entropy level. And so our gain simply, again, is just entropy 1 minus entropy 2. And of course, we've got our root node, the topmost decision, and we've got our different data sets. So we've got this entropy for set 1 and set 2. They're both set to entropy 2. And we've split this data, right? So we have what we call these decision nodes. Okay, so there's 2 or more branches. And of course, we can split data set 1 and data set 2 again, right? And this is really what it looks like. We randomly see what's in the data set and we split that up. And you can see how it's subdividing or splitting as we go through each level of entropy here. Okay, so with random forest, okay, here's an example. So you got to follow along with this example here because it's a pretty good example of random forest. You know, go back and review this if you really need to, but I'm trying to simplify this the best I can. So I've got this bowl of fruit, okay, and it's high entropy. I've got cherries, apples, and lemons. Okay, and I've got these different conditions. So in my conditions, I'm saying that my color is dark red. Okay, the diameter is greater than or equal to 3. Is our color yellow? Is our color red? Is the diameter less than or equal to 1? Okay, and so we can put that again into a chart. And as that goes into the chart, you know, I'm looking for certain things to stand out. And this is where maybe I introduced a little bit of bias, or, you know, your result is going to be a little bit different than mine. And so when I look at this particular chart, though, What's nice about this is that, it gives me a really good hint as to where I can start, because this condition is going to give me my maximum gain, whether you want to be subjective or not with this. This kind of tends to steer a little bit towards a little bit objective, if you can kind of buy into that argument. So I'm looking here and I'm saying my diameter is greater than or at least equal to 3. Okay, so that is the condition right now that's going to give me my maximum gain. Okay, so when I look at this, I say, okay, is the diameter greater than or equal to 3? I know that it splits, right? So everything is going to, my cherry is going to be false, clearly. It's not going to be bigger than 3, but my apples and my lemons will. Okay, so this node here with the cherries now is already at 0. I can't split it anymore. But this node over here requires further splitting to get to my 0. Okay, so, entropy after splitting has decreased significantly after the splitting. Okay, so then what happens? I'm in this situation again. I've just kind of reversed the cherries and the apples and lemons here. Okay, but, I've split the data based on that one condition. Okay, now what I have to do is further split the entropy level that needs to be split even more. So I can look at this and say, okay, the cherries I don't need to split, but the other node I need to split. So I can say, is it yellow? And then that will split again into false and true. Okay, and this node is already at 0, so no further splitting. Okay, so entropy after splitting has decreased again, right? Which is a good thing. This is what we're hoping for. And so we're going to say that this is now, we consider this tree 1. Okay, this is tree 1. And so, now we have this other scenario here. We've got, is the color red, true or false? And, you can see on the right that the cherries and the apples are red. But then the next thing is, are they dark red? And so, cherries are truly darker red. Apples are lighter red. And so we're going to call this one tree 2. This is the result for tree 2. And now we can look at other conditions here. So is the diameter less than or equal to 1? And so you can see that, yes, the cherries are, but the apples and the lemons are not. But then can we say that they're grown in the north? Now, I'm pretty sure you can grow an apple in the north. I've seen it, but I don't know that you can grow an apple in Canada. Okay, so we've got that condition right there. So you can see that our entropy is dropping along this side. And so we're going to refer to this as our tree number 3. Okay, and if we look at them all here, you see we've got tree 1, tree 2, and tree 3. Okay, so let's look at this example overall again. We've got this unknown object, and we know it's an apple. So we're trying to predict, this is what we're using our random forest to try to predict if we have an actual apple. Okay, so if we look at this, we say, is it greater than or equal to 3? Yes, that's an apple. These are the conditions for an apple, but we're trying to predict if it is an apple. Okay, is it red? Is it grown in the north? And is the shape a circle? Okay, so these are all the things that we're the conditions that we're going to compare this thing to and determine whether or not it's an apple. Okay, and so we go through this whole chart, and by the time we filter through our random forest, okay, in tree 1, we decide that yes, this meets all of those conditions. Okay, and then we look at it again through the different tree 2 parameters. And by the time we filter it down and we're looking ultimately at the lowest leaf node for the lowest true result, we can see that tree 2 predicts this to be an actual cherry. Okay, and so when we go again, we look through all of our conditions again, and we filter down and we're looking for the lowest level true. You can see here for tree 3 that it does in fact predict that we've got an apple. Okay, and so what does this really mean when we sum this all up? I've got tree 1, which says it's an apple. I've got tree 2, and it says it's a cherry. And then I've got tree 3 that again says it's an apple. So the majority of these, okay, we can classify this apple. You know, is it going to be a cherry or is it going to be an apple? And the majority says that it's an actual apple. So apple must be true. Okay. And so let's get back into our anaconda and look at another example. And I'm going to do it. I'm going to actually use the iris database to predict the species of flowers. Okay. I'm going to go ahead and do that right now. So, you know, I suppose in the machine learning world, using the iris data set is almost akin to Hello World. So, you know, we'll do this. We'll have the rite of passage with the iris data set. And so I'm going to, you know, put it in a comment here. And that we're going to load in the library with the iris data set. So you've seen in other cases where I'm actually including. So in the last example, I went and I grabbed the data set from a CSV. But in this case, what I'm going to do is I'm going to go to sklearn and I'm going to get their copy of the data set. So this is going to be from sklearn, and it's a .data set with an S, data sets. And we're going to say import load underscore. Let's see what it says with the tab. Doesn't seem to be giving, oh, there it is. Okay. So it's right down here. I'm going to go with load iris. But what I want to do is point out that sklearn has load Boston, breast cancer, diabetes, digits, files, and all these different examples here, right? Load wine. So right now we're going to use the iris data set for this. Okay, and then down here, what I want to do is load the random forest. I'll put the comment in here. Load the random forest classifier library. Okay, so remember in this example, we're doing random forest. And so this is going to be from sklearn dot in its ensemble. So just like this, sklearn ensemble. Okay, so I'm going to select that one and we'll say import random forest classifier. So if I go to R tab, there it is. So I've got random forest classifier, random forest regressor, or trees enabling. So I want the classifier, the first one there. Okay, now the next thing I want to do. So now the next thing I'm going to do is I'm going to load my pandas, and I want it because I want this to look like a spreadsheet, and I'm loading NumPy. So if I say import pandas or NumPy, doesn't matter, pandas, pandas as PD, this is typical stuff we always do, and import NumPy as NP. Okay. Second thing I want to do is now, or the next thing is setting my random seed. Okay, setting random seed. Okay, and we'll do this with np.random tab. See if the tab, okay, good, tab worked. Dot seed, and we'll just put a 0 in there for now. That's all I'm going to do. Just want to know if you guys are aware of where this iris database came from. So I guess in the 30s, this came by somebody to predict the species of a plant just based on the dimensions of the plant itself. That was the criteria used to predict what it was. And so this entire database was created. So yeah, it's interesting to me that since 1936, this iris database has existed. And I guess the researcher's name was Ronald Fisher, who created this. And you know, the great thing is the benefit of this work, it became so popular. Now we get to use the module from sklearn to do what we want to do, at least to learn this particular skill with random forest. So I think that's pretty cool. So thanks, Ronald Fisher, wherever you are. One thing I should probably do is just rename that iris. There. Okay. Okay, so anyway, we've got it all set up to this point with everything I want to do in this cell. I'm just going to run it. It shouldn't show me anything good. So the bigger picture here is that I'm not getting any errors. Okay. So the first thing I want to do now is create an object called iris with the iris data. Okay, and so we're going to say load underscore iris and put that as a function. And then now that we have that, we're going to assign it to iris. Okay, and we've got that now that we can use. And the next thing I want to do is I want to create a data frame. Let me put that in there. I'm going to create a data frame with the 4 feature variables. Okay, and so this is going to be pd dot data frame. Let's see, data frame right there. It's in the tab. And we're going to say iris.data data. Didn't pick it up. That's okay. Iris.data, comma, columns is going to equal iris dot feature feature. Okay, my tab didn't pick that up. That's okay. Feature underscore names. Okay. And what do we want to do next after this? What I think I want to do is just look at the top 5 rows from here. So really, we're just going to view the top 5 rows with, you guessed it, df head. Okay. df dot head. And that's a function. Okay, and I've got one more comment that now I'll leave that out, but let's just have a quick look at this. I'll run from the top, run from the bottom. You can see that I have this particular error. Okay, and that's okay. And the reason is because up on line 5, I didn't assign it once I created that data frame. So I need to assign data frame just like this, and now I can run this. Okay. And so you can see the 4 columns that we have that we really matter to us. Okay, so we've got sepal length, width, petal length, petal width. Okay, so we're good if we're to this point. So now the next thing we want to do is copy a new column for the name for the species name. Okay, and we'll say. We'll do it like this, df, okay, square brackets, and inside here we're going to do our quotations and say species, species, and then that is going to equal pd dot categorical. Okay, so the word categorical, it's in the tab, categorical dot from codes. Okay, so from codes, and then in here in this bracket, we're going to say iris. Okay, iris dot target. Yep, the first one's target, and then we'll do a comma and say iris dot target, and this time it's target names. Okay, and so now we're going to view the top 5 rows by default. Okay, and again, that's just calling the head function again, but I'll put a note. And we're just going to do df dot head bracket. Okay. And so let's see if there's any changes in this. All right. So now what we've got is this new column, and it's titled Species. So this is good. It's just adding more content to what we already had. Okay, we can visually see this better now. And so now what I want to do is actually create, test and train the data. So in the next cell below, what I'm going to do is create, test, and train data. And the way I'm going to do this is I'm going to add another column. So if I say df, and in here with the single quotes, say is underscore train. Okay. And then I'm going to, do the right hand side of this. So I'm going to say numpy dot random dot uniform. Okay. And then with uniform, what this is going to be is 0, 1, length. So I've got 0, 1 length, and then there's one more thing that I need to grab. And it's just, this is a function call for length. So in here, we're going to say, what's the length that we want? And I want the length of df. Okay. Now I'm going to go outside of the bracket here, and I'm going to say is less than or equal to dot or 0.75. Okay, so I'm just going to leave that set to that. And then again, I'm just going to look at the top 5 rows. So I'll copy this into here. Okay, and let's have a look at this again and see what's going on. So very briefly, what I want to do is say we're going to, I'm going to explain this a little bit. We're going to generate a uniform random number between 0 and 1. Okay, and we're going to do it for each of the rows in our df. So that's really what this line of code is right there. So if it's less than this 0.75, then it's true. If it's less than or equal to 0.75, then it's true. If it's greater than that, then it's going to have a number of false. So now really what I'm going to do is just create this data frame with test rows and training rows. Okay. And so what we'll do with this one is we'll handle it in a couple of different steps here. First off, I just want to get the logic right before I start assigning it to things. So what I'm going to do is this df, okay, square brackets, go back inside the square brackets. So df again, and square brackets. And in here, we're going to put our single quotes, and we're going to say is underscore train. Okay, and then we'll go outside of one set of those brackets and say equals true. Okay, and remember, equals is a comparison. And so now I want to do the next one. I want to say df again. In fact, what I can do, probably the most efficient way of doing this is just to take it all, copy it, paste it on the other side of that comma there. And I'm going to say that this one is false. Okay. And what do we want to do with all of that stuff? So the first thing I need to do is assign it to something. And by assigning it, what I'm going to do is say train, comma, test. Okay. So it may seem a little bit odd that I would be taking two different things on the left-hand side and then with a comma, but I can assure you that this syntax is actually perfectly okay with Python. Okay. So if you kind of bear with what the logic is saying, it's like in grammar where you name a list of things and then you say respective. So what this means is this first train here has the output of this operation here on the right side. If that condition becomes true, then you assign it to train. If it's false, as in this operation here, then you assign that over to test. Okay, so that's really, it's almost like a shorthand of programming in terms of Python. Okay, so now the next thing I want to do is show my, let me move this up so I've got more room. And I'm going to show the number of observations for test and training data frame. Okay, and the way I'm going to do this is I'm going to print. And inside my print, I'm going to say single brackets, number of observations in the training data, number of in the training data. I'll put a colon there. Of course, I'll spell the properly. Okay, and then on the other side of that, after I give it a space, I'm just going to say len, length of train. Okay, and then that should be this, but now I also want to do for the other. So I'll copy and paste this, and not for training, but for testing. For testing data. And this should be, you guessed it, test. I do this sometimes as a confirmation, even though I can see that it's spelled the same way. And so let me go ahead and I'm going to run it all from the top. Okay, sometimes it's best just to do that. It's almost like doing a build and then a run in some of the other IDEs that you may have used in the past. And so now what you're seeing here is that the number of observations in the training data are 118. The number of observation in the testing data is only 32. Okay, so that's not too bad. Okay, so now we're gonna, in this particular case, create a list of feature column names. Now I'm gonna say feature with an S, so this will be plural. And we'll say df dot column, do the tab, and in here we're going to say colon 4. Okay, and then let's, how about we view features. So we're going to view the features. Okay, and all I'm going to do is a print my features. That's it. And let's have a look and see what that is. Okay, so this is what we expected to see. So we've got this feature, the length, the sepal width, petal length, petal width. We're good. All right. So at this point, we're actually pretty happy. Now, what I want to do though at this point, okay, is I need to convert the specie names into a digit. Okay, it's an important step that we have to do. We've got to try to convert these things into digits, because how do we take literally an image or a set of measurements or whatever and convert them into something that we can now manipulate or use? And, you know, in the last coding example that I did in this video where we were looking at the bank loans, you know, I did the same sort of thing. I converted whether a person had owned their own home or if they rented. I converted that into a yes or no, meaning a 1 or a 0. But in this case, what I'm going to try and do is make a representation based off of 0, 1, and 2. Okay, so let's have a look and see what that's going to come out like. Okay, and I'm actually going to put I'm going to put a comment in here as well. Just before I do this. So I've got 3 species that get converted to 1, 2, or 3. Okay, so that's what we're going to do. And, you know, we're trying to get a prediction. So our output is going to be Y. And it will be pd dot factorize. And this is a library function, factorize, that comes with sklearn, or pandas, sorry. And in the brackets, what we're going to do is say train and again inside, not round brackets, sorry, it should be square brackets, because we want that label that we had up here that we created, this right here. Okay, so that's what we're looking for. So inside there, I'm going to say species. Okay, and then I'll go outside of that. And here, I'm going to define this as the very first one. Okay, and let me come back to this in a minute, because now I want to view target. Okay, to view target, that's simply going to be Y. So this is kind of an array of an array, and we're going to start at the 0. And that's why with this particular code, we're starting with the square brackets of and we're at 0. Okay, and factorize is going to help address this issue. So 1, 2, and 3. Okay, and remember, we've got 3 species. I don't know if there was anywhere in here where we looked at the different names of the species, but basically there's Setosa and the 2 other species of plant that we were looking at. And so what we're doing is by converting those into 1, 2, or 3, this factorize is going to actually help with that. And I know that's not the greatest example you would expect, but let's just run this and see how this actually looks. Okay, so if I go to here and I run that, you can see now that, one of my species is defined as 0. The other species is defined as a 1, and the final species within the data set is now identified as a number 2. Okay, so that's really what we're doing with factorizing. So this whole line of code is really meant to just factorize it into, instead of giving it a string name like Setosa, it's now just assigning a number to it. So that's the whole point of that. So at this point now, what we can do is create a random forest classifier. And it's amazing how little we have to actually do for this, because the library functions are actually going to take care of that for us. So if I do ran, you can see I've got these things. So I have to be specific with my capitalization. So random forest classifier is what I want. And it's a function. So inside this function, what I'm going to do is say n underscore jobs. And it's one of the library functions as well. So n underscore jobs equals, and for now I'm going to pick 2. And I'm going to say a random state is going to equal 0. So in this particular case, this n jobs is kind of a default setting. There's a lot of different arguments that you can pass through this random forest classifier. But this one is kind of a typical setting that you'll use often. And, right off the bat, we're just going to set that random state to 0. So these, for the most part, are just kind of your typical default settings. So we will set this CLF for classifier. So we'll do that. And then the next thing I want to do is I actually want to train that classifier. Okay. So if I do this, it's actually not a lot of code to get to this point, but clf.fit. Okay. And then inside the fit, we're going to say train. And again, more square brackets. We're going to say feature. Okay. Or features. And then comma, our target is Y. So all this stuff here is our target Y right here. Okay. And so really that's all we're doing with this particular one. And I can go ahead and run that. I'm not going to get much of an output other than to show what's kind of already going on there. Okay. And so believe it or not, we put a lot of work into just getting to this point, but we're not seeing much of a result yet. Okay, so right now, what I want to do is just kind of look at the features here. Okay, and so we're going to say test square brackets features. All right, and then I want to apply the training classifier to the test. Okay, and let's let's put the comment in there. And we're going to say CLF dot predict. Okay, predict. And inside predict, we're going to say test, square brackets, we're going to say features. Okay, and that's it. That's what we're going to do for that. So let's go ahead and run that right now. Okay, and so our prediction's kind of interesting. Based on our training set or our data set, this is sort of the prediction of what's happening here. But I'm sure you're looking at that and saying, well, it's kind of meaningless to me. So definitely I didn't explain this one very, very clearly, but the point of this was to try to show this in two different ways. So if I comment out this line right here and I run this, you can see that I'm getting different output than you may have expected, right? And you'll notice that the numbers, there's gaps in the numbering here, right? So this is kind of one way you can look at that. If I just wanted to look at the features themselves based on the prediction, okay? And so that's kind of why I did that. But if I uncomment that out, okay, and let's say I comment this one here, and I run this again. So now I've just got a different look to what's going on. Okay, so really that's the only the thing that I was after with this. So I can uncomment that and run that again. So we know based on this that we've got this prediction based on the classifier up top. Okay, so this whole cell up here is what we're using to make the actual prediction right here. And this is ultimately what the output is. And remember what these mean, right? It's predicting that all of these are Setosa. I can't remember what the other two are. Anyway, but 0 is Setosa. So it is predicting that that's what that is and the other flower types. And you can see that they're mixing, right? They're not all just sort of in this same order that they're not sorted is what I'm trying to say. So, another thing that I can actually do here is we can view the predicted probabilities for the first 10 observations. Okay, and I'm going to walk through what that really means. So if I say CLF dot pred, okay, and I'm going to hit tab, and I've got a couple things here. And we've used predict up in the previous cell, but here I'm going to say predict probability. What is the probability here? And in this case, it's a function, so I can go test, square brackets, features. And outside of that, I'm going to say just look at the first 10, okay? And so when I run this, I'm going to get this in a different looking format, right? And what is this saying? This is saying that the probability that the very first one is, I think we call it Setosa, and that the next one is not, and the next one is not. So, these were sort of the leaf nodes that we were going through. So if we remember, think back to the slides, and we're trying to distinguish whether something is a cherry versus an apple, right? This is what we're talking about. So it's saying that the first one, and this matches up with what's happening right here too, right? So it's saying that the probability, so if we say 1, 2, 3, 4, 5, 6, so 1, 2, 3, 4, 5, 6. So this one here is, the probability is about 0.95 chance that it is actually Setosa. Okay, so this one here is 0.99% that this one here, I think, is Setosa. Okay, so that's really what we're saying in that particular case. Okay, because I can go in and actually change these. If I were to change this to 10 and this one to 20 and then run this, right, now I'm getting a different combination of the values. Okay, so this is really what we're doing here. What is the probability that I'm getting the right accurate prediction? And that in itself is super powerful with what we're doing here right now. So let me change that back to, doesn't really matter, but I'll just change it back. So let's go to the next thing and say, let's map the names, okay? Because I can't remember what the names of these things are. So I'm going to map the names of the plants for each predicted class. And we've got Setosa. That's the only one I can seem to remember, to be honest with you. So we're going to say, iris dot target, and we'll say target names. And in here, we're going to say our classifier CLF dot pred. And so predict, in round brackets, we're going to say test, and square brackets, we're going to say features. Okay, and all of that is going to get assigned to, we're going to just call this preds, predictions. Okay, that's what we're going to do with that. And so the next thing I want to do is I want to just view those predictions, right? And how do I want to do this? I want to say preds, and just I want to look at the first 5. Okay, and let's see what happens. Okay, so you can, as you can see, the first 5 were Setosa. All right, which is 1, 2, 3, 4, 5. So, that's pretty good. Do we want to check something else? I don't know. Let's check 15. I don't know. Just as a guess. Okay, so Versacolor, Setosa, and then Versacolor. Let's try 10 to 25 and see what happens there. Okay, so you're getting Setosa, Versacolor, and however you say that word. Anyway, so that's kind of how we're mapping what our predicted output is with the actual name of the plant. Okay. Okay, so I'm gonna change this back to 0 and 10. Okay, and I'll rerun this. Okay, we're good. So now what I want to do is actually let me view the actual species for the first 5 observations. And so we're going to say test, square brackets, and in here under these single quotes, species, and it'll be dot head. Okay. And as you know, head usually just gives you the first 5. And I think that's something actually from Unix or Linux. So what does that give us? It is predicting the first 5. Okay. And you can see the first 5 that are Setosa. Now that's interesting, right? Which is saying that sample number 7, 8, 10, 13, and 17 are Setosa, which is pretty interesting. And, these are the 3 options: Setosa, Versacolor, and Virginica. All right. Okay, so the next thing I want to do is to confuse you more with the confusion matrix. Now, I touched on this the last time we did a video on decision trees, but maybe we can explain it a little better now. So in this case, what I want to do is I want to say pd dot cross tab. Okay. And in here, I'm going to say test, and square brackets with single quotes, we're going to say species. If you learn anything at all whatsoever from this video, it would be the proper spelling of the word species. Okay. Preds. Okay. Comma. And we're going to say row names. ROW tab equals row names. And in here, we're going to say actual species. Okay, and then a column, and I'm going to say, a comma, and then column names. Column names is going to equal square bracket, quotes, predicted species. Okay, and let's have a look and see what that sort of outputs to our screen. Okay, so we've got our predicted species, these three here, and then our actual species. So we've got Setosa, versicolor, virginica. And so what the confusion matrix is saying is that, okay, so this crosstab, what crosstab is actually doing is it's taking two different things and combining them into one chart. So you've got your predicted species and you've got your actual species. And so where the predicted and the actual meet, we see that 13 times Setosa was accurately predicted. Okay, and you see here that versicolor was 5 times predicted accurately versus the actual. Okay, and virginica was the same thing, but in this particular case, we have 12 times where those two things matched up. Okay, so this column matched up with this row a total of 12 times. Now, if you were to add all this up, 13 plus 5, which is going to get you 18, okay, plus 12, the end result of that is going to actually be 30. Okay, so the number of accurate predictions here is 13 plus 5 plus 12, which is 30. That's the number of accurate predictions. But you can see that we have a 2 right here. So we know that this was wrong. The answer to this wrong is wrong. So the predicted against the actual was wrong 2 times. So out of all of these samples, we've now got a number of inaccurate predictions was a total of 2, and the number of actually accurate predictions was 30. And so what we have to do is count up all of them. So we know that 30 plus 2 is 32. And so, you know, if we looked at this as a test, we would say, hey, I got 30 out of a possible 32. So your accuracy is going to be 93. Okay, so that's kind of how we're able to easily calculate our model's accuracy. So the last thing I want to do, or that I can do here, why not, is I can just input dimensions to anything that I want and then see if I get the right output, right? So I can say iris, like if I literally type in my own actual dimensions to this. And what I can do is say clf.predict. Okay, predict round brackets. Now I could just take random numbers. I could say 5.0, comma, 3.6, comma, 1.4, comma, 2.0. Okay, so I can do that. What I'm missing here is an actual square bracket. Okay, and I'll put in another square bracket here. Because let's say I want to do an array of arrays. I want to actually have 2 different measurements. Now that I've got the model built and it seems to be relatively accurate. So now I can say 5.0, comma 3.6. See if I can mix this up a little bit. 2.7, comma, I don't know, 3. Okay, and is that finished off? It doesn't look balanced to me in terms of my bracketing, so I should fix that and then finish that off. So it looks like I shouldn't have that. I've got a red error on there and seems okay. So let's, I should actually assign that now, and I've done that before. Preds equals. Okay, now let's see if this gives us a prediction when we run this. Okay, so there it is. Based on this information that I'm manually typing in, my model's actually able to correctly predict a good output based on what these are. Okay, so that's pretty good. I'm quite happy with that. So one final thought that I want to leave you with is, how do we determine if our model is good? Okay, and because we have our larger training set with our test set. And I guess the most simple answer to this really becomes, it depends whether you're doing regression or classification. Okay, that's really what it's going to boil down to to determine whether or not you've got the best model or not. Anyway, what I want to do is end the video there. And hopefully you followed along with this. And maybe you've done some of the code example on your own just to get a feel for what's really going on here. But anyway, I'm just going to leave it there because I don't think much more that's worth trying to cover or expand on. I went into some pretty good detail, I think, on the theoretical part, and we looked at how the theoretical part, as complicated and messy as it can really be simplified. But then when you do the programming piece, it actually gets even more simplified because there are all these excellent library functions that can handle all the heavy lifting for us. Okay, so anyway, I'm going to leave it there. Thanks for watching, and I will see you in the next video.